So we stopped at this equation that is called the Dirac's relativistic equation, which we can write again as, let's say, I h cross dou psi by dou t is equal to minus I c h cross alpha x dou by dou x plus alpha y dou by dou y plus alpha z dou by dou z psi plus beta m c square psi. Now we haven't said yet what these alphas and betas are. So we already know that the alpha x square is equal to alpha y square is equal to alpha z square is equal to beta square is equal to 1, and of course alpha x, alpha y, alpha z and alpha z, alpha x, all these are anti-commutating. So we said that these properties may lead to assume that the alphas and betas are, or alphas are rather, some form of polyspin matrices. Now we know that the Hamiltonian we wrote as C alpha dot P plus, maybe these are two vectors, plus beta m c square. ഇതാണ് നമ്മൾ അതിൻ്റെ റൂട്ടായിട്ട് ഇ എന്ന് പറയുന്നതിൻ്റെ റൂട്ടായിട്ട് എടുത്തത്. സോ ദാറ്റ്സ് എ ഹാമിൽട്ടോണിയൻ. ക്ലിയർ? നൗ every Hamiltonian in quantum mechanics has to be Hermitian. So that means alpha dot p, that means alpha xpx plus alpha ypy and so on. So we know that the alpha x, alpha y, alpha z and beta, these all has to be Hermitian. Okay, and of course we know that the alpha square, alpha x square, alpha y square, alpha z square and beta square, all these are, the square of all these matrices are unity. So from these we can know that the eigenvalues of these matrices are, see, alpha x square is plus 1, so the eigenvalues are plus or minus 1 should be. Okay, so if you know how the eigenvalues work, then can say that since alpha x square is equal to 1, then its eigenvalue should be plus or minus 1. Similarly, alpha y, alpha z and beta. I can write alpha x is equal to alpha x into beta square, no problem, because beta square is equal to 1. Now that I can write alpha x is equal to alpha x beta square is equal to alpha x beta beta. That's also possible. Now since beta is Hermitian, I am taking it to the pre-multiplication point, so that I can write alpha x is equal to minus beta alpha x beta, no problem, since these are Hermitian. Now trace of this is equal to trace of this. Okay, you know trace means the sum of diagonal elements. So now I can write that is trace of ABCD, let us say ABCD, മൂന്ന് മാട്രിസസിൻ്റെ പ്രൊഡക്റ്റ്, 4 മാട്രിസസിൻ്റെ പ്രൊഡക്റ്റാണ്. ഓക്കെ, സോ അതിൻ്റെ ട്രേസ് ആണ് നമ്മൾ എടുക്കുന്നതെന്ന് വിചാരിക്കുക. സോ ദാറ്റ് ഈസ് അഗെയിൻ ഈക്വൽ ടു that would be equal to, by the matrix properties, that would be equal to decan cyclic order. Okay, so the D, A, B, C, and any cyclic order, no problem. So if I follow the same here, trace of alpha x is equal to trace of, okay, okay, so I'll be taking this as the cyclic, okay, so cyclic angle alpha x beta square minus is there, okay. So this minus trace of alpha x beta square, that is equal to minus trace of alpha x. Clear? Now something here, what is that? See, the trace of some matrix here, the negative of the trace of that, both are equal. So there are only limited probabilities for that. That means either all the diagonal elements should be 0, or if these are not diagonal elements, then the order of this matrix should be even. Okay, because we have this policy spin matrix sigma x as 0, 1, 1, 0. Okay, leave it that. Just a minute. I don't know. So here, okay, we can say it in another way. So the sum of diagonal elements would give you 0. Okay, so because it should be like this. See, you have something negative is equal to something positive. That's only happens when you have a 0 sum diagonal elements. Now the sum of diagonal elements is also plus or minus 1, because the eigenvalues are plus or minus 1. So what happens is that ഈ പ്ലസ് ഉള്ള ഏജൻ വാല്യൂസിൻ്റെ അത്രയും തന്നെ മൈനസ് ഉള്ള ഏജൻ വാല്യൂസ് കൂടി വരണം. That means that simply it should be an even number. Okay, now we have the sigma x, sigma y and sigma z. These are 2 by 2 matrices. Okay, we know that. But there is a problem that we cannot find a fourth matrix that is anti-commutating with these 3. അതുകൊണ്ട് പിന്നെ നെക്സ്റ്റ് പോസിബിലിറ്റി എന്താ ഉള്ളത്? It should be some 4 by 4 matrix. Okay, leave it, don't worry about anything. So what we derive here is we will be using alpha x is equal to simply sigma sorry, so 0 sigma x 0 sigma x, sigma x 0, sorry. So that should be the sum. So that means what is sigma x? 0 0 0 0 sigma x എന്താണ് 0 1 1 0 അല്ലേ? അതുപോലെ sigma x എന്താണ് 0 1 1 0 0 0 0 0. So this is alpha x, and alpha y is similarly 0 sigma y 0. What is sigma y? 0 0 0 0. Sigma y എന്താണ്? Simply 0 minus I 0 0 minus I 0 0 0 0 0. And similarly sigma z is equal to ഓർക്കാൻ എളുപ്പമാണ് അല്ലേ? 0 sigma z 0, or that is equal to 0 0 0 0 sigma z is 1 അല്ലേ? 0 0 minus 1, then 1 0 0 minus 1 0 0 0 0. So this is sigma x, sigma y, sorry, this is not sigma x, alpha z. Okay, so alpha x, alpha y, alpha z, and of course we have the beta. Now what is that beta? Obviously we will be taking it as 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 minus 1. So this is the, otherwise the diagonal element sum cannot be 0, I mean the trace cannot be 0. So these are the alphas and beta. So these matrices are known as Dirac matrices. These are all 4 by 4 matrices. Now since the alphas and betas are 4 by 4 matrices, the psi also has to be 4 by 4, I mean a column matrix of order 4, psi 1 psi 2 psi 3 and psi 4. Okay, so don't worry about all these things. Now sometimes these 4 matrices, that's alpha x, alpha y, alpha z and beta, these are also known as Dirac spinors. Okay, so these are the 4 Dirac spinors or spinners. Okay, so that's the one case which we wanted to finish. Okay, before that let me go to the Wales equation. Okay, that's a little bit important equation, Wales equation, that's there in your syllabus also. So let's go for the Wales equation. I think that's the spelling. Now let's consider the Hamiltonian. What was the Hamiltonian which we have derived here? See, this is the Hamiltonian. Okay, so now for a massless particle like a neutrino or something, okay, so for a massless particle or a zero mass particle, the Hamiltonian can be written as Cp or Pc, whatever. Hope you remember, I mean the energy was something like root of p square c square plus m square c raised to 4, where m is the rest mass. So always remember that if the rest mass is 0, then this is not there, so this is Pc. Okay, so H is equal to Pc. Now the same Hamiltonian in the Dirac notation was C alpha dot P. Okay, hope you remember alpha dot. So now you have a alpha here. You compare this. So here the alpha, which is a vector operator, which we have derived here, these alphas should be independent of the space and time coordinates. Should, of course, നമ്മൾ നേരത്തെ കിട്ടിയാണ്. Anyway, should be independent of space and time coordinates. Obviously, it should be some matrices of this form anyway. So anyway, so C into alpha dot P. Now, what would be that? Obviously, see, this should be equal in that case. So we can write alpha dot P should be something like sigma I is equal to 1 to 3 pi square, or simply that is px square plus py square plus pz square. So that is p. But p avanaengil alpha dot p is equal to this. Clear? Okay. Now let's square it. Alpha dot p square is equal to sigma I pi square. Good. Now, if I take the square root of this onto one side, then I can say the alpha dot p could be something like there could be a minus also or a plus also of the momentum. Okay. Now, what can we do with this? Let's consider the negative. Okay, so H is in that case is equal to minus C alpha dot P. Okay, so when I write the E psi is equal to H psi, that is the Schrödinger's equation, then I can write E psi is equal to plus or minus C. Okay. Let us write alpha dot P psi. Okay. So if I write that in the coordinate form, I mean in the usual operator form, dou by dou t, dou t of psi is equal to minus I h cross C alpha dot P psi if ഇവിടെ പ്ലസ് മൈനസ് ഉണ്ടല്ലോ, അപ്പോൾ പ്ലസ് ആണെങ്കിൽ ഇഫ് ആൽഫ ഡോട്ട് പി ഇസ് ഈക്വൽ ടു മൈനസ് പി ആണെങ്കിൽ, അതർവൈസ് എന്തായിരിക്കും, ദിസ് ഈസ് ഈക്വൽ ടു ഐ എച്ച് ക്രോസ് സി ആൽഫ ഡോട്ട് പി psi if alpha dot p is equal to plus p ആണെങ്കിൽ. ഇങ്ങനെ രണ്ട് ഇക്വേഷൻസിന് എനിക്ക് കിട്ടും അല്ലേ. These two equations are possible, and these equations are usually known as the Weyl equation. Okay, these equations are known as the Weyl equation. Now let's move on to the last portion maybe, that is